All right, gonna redo here 3.5 to make sure we have this done. So first page here is some trigonometric identities and functions and things. You need to make sure you remember these, that you know these basic ones. They're gonna be useful to us, and also some trigonometric limits here. Some ones we did and even where we did them back before. So make sure you know these and you're familiar with these, and even like this that we're going to use. That's a good one to make sure you know this page pretty well. All right, so let's get into this. Let's take a look at the function sine of x. And so what we want to do is find the derivative using the limit definition. So we're going to start with f prime of x is equal to the limit as h goes to 0 of the sine of x plus h minus the sine of x. So this just comes from our f of x plus h minus f of x all over h. And now we need to actually go through and do this. So what we can do is do limit as h goes to 0, and we can take advantage of just what was on this previous page, this right here, sine of a plus b right there, and what it equals to. And so we can expand out that sine of x plus h, where x is a and h is b. This will become sine of x times cosine of h plus cosine of x times sine of h. And then we still have that minus sine of x all over h. And next we could take a look at this, and what we can do is we're going to bring this sine of h over and group it with that first term. And so we'll end up with limit as h goes to 0 of sine of x times cosine of h minus sine of x plus cosine x times sine x, like that. Okay, and then, not cosine x, sine x, cosine x, sine of h. There we go, all over h. And so here in the first part, we have a sine of x that we can factor out. So limit as h goes to 0, sine of x times cosine of h minus 1, and then plus our cosine of x sine of h, still all over h. And then what we can do is break this into two limits. So we'll have the limit as h goes to 0 of sine of x times cosine of h minus 1 over h, just like that. So we're doing this limit, plus the limit as h goes to 0 of cosine of x times the sine of h over h. Okay, just like that. Now we're taking the limit as h goes to 0, and if we look on the previous page, the limit as h goes to 0 of cosine of h minus 1 over h is 0, and so we have that right here. This sine of x is just a constant as far as h is concerned, so we just can bring it out front and not even actually do it. So we're actually taking the limit just of that part that has h in it. And so this goes to 0, which means this whole thing goes to 0. Plus, over here, again, this cosine of x can come out in front because it's a function of x, not h. And so then we just have the limit of sine of h over h, which, as we did previously, is just 1. So this goes to a 1, which means we have just cosine of x here, which means ultimately our derivative of the sine function is cosine. There you go. Derivative of sine is cosine. Now you don't want to go through and do this whole limit out. I mean, I'm assuming you don't want to go through and do this whole limit out every time. So this is one you're just going to want to memorize. The derivative of sine is cosine. Okay? And so then here's a couple little examples. Find the derivative of the following functions. So we have derivative of x squared minus sine x. So the derivative is just going to be 2x, and then derivative of sine is cosine, so minus cosine x. So that one's not hard. Over here, we've got the derivative of two functions multiplied together, e to the x and sine x. So this is our first one, this is our second one, right? And so it's derivative of the first times the second plus the derivative of the second times the first. So this is just going to be the derivative of the first one is e to the x times the second one plus the first one times the derivative of the second one. Derivative of sine is cosine x. And there you go. That's y prime. There you go, one line. Get that written out. You could actually even take this one step further and factor out an e to the x. Just like that. Be careful. There you go. Those two are equivalent answers. Be careful. This is not 1. This is not sine squared plus cosine squared. Don't make that mistake. Sine plus cosine is not 1. All right, the next one, this here, I want you to try. Just keep in mind that cosecant is 1 over sine of x. So give that one a try, and then you'll be able to find the actual solution to it in the notes. All right, here we want to look at the derivative of the cosine function. Now, derivative of sine was cosine, so do we think maybe the derivative of cosine is going to have something to do with sine? Well, let's take a look at this. So here, instead of doing the whole thing out with the limit, which you could do, you could go through and do it with the limits, very similar to what we did for sine. But here we're going to just kind of look at it visually. And so let's take a look at some of these slopes. If we start over here at negative pi, we have a slope of 0. So if we come down and put a point at 0 right there, then you look here, and here we have a slope at negative pi over 2, we have a slope of 1. So you come down here, and you get a 1 right there. Then you go up here, and you're back to a slope of 0. So you go back to a 0, right? Then you have a slope here equal to negative 1. So there's your negative 1. And then you have a slope here of 0 again. So you're back to 0. And if you look at this, this is the function cosine x. What is this function down here that we're following right along with? That's actually the function negative sine of x. So it turns out that the derivative of sine is cosine, but the derivative of the cosine function is the negative of the sine function. All right? That's what it is. So we'll write it over here. Derivative of cosine of x is negative sine of x. And again, that's one you're going to want to memorize. Okay? So let's try one of these. I'm going to leave the second one for you to try, but I'll do the first one right now. So this is y prime. Derivative of the first one, 5e to the x, is just going to be 5e to the x. E to the x ones are the easy ones. Then the derivative of cosine is negative sine, so this becomes minus sine of x. And there you go. All right, try this next one yourself. You're going to have to use both the derivative of sine and derivative of cosine, and get your answer using the product rule. Whatever you do, this answer is not going to equal 1. So if you do something where you think it's 1, then you're going to want to look in the notes and see where I solved it and see that it is not equal to 1. I'm going to leave this one for you to try as well. Similarly to the cosecant one, think about what secant actually is, and figure out then what the derivative of secant is. Later on, you may be one that you also want to memorize the derivative of cosecant, derivative of secant. But if not, if you don't memorize them, you can always just do them out if you do those practices here. All right, here's an example of this being useful. It's called simple harmonic motion. This is something that you probably would have seen if you ever taken physics in high school or college or anything. You would have seen this. This is basically anything that follows what is called Hooke's law. And Hooke's law is just the statement that F equals negative Ks. And so what this is going to do is it's motion of an object that follows that, where the force acting on it is in the opposite direction, where S is the displacement, the opposite direction of the displacement, and then k is just some constant dependent on the situation. A spring with a mass on it is an example of simple harmonic motion, and it is a type of periodic motion. Not all motion is simple harmonic, but the ones we're looking at here are. So here we have a weight hanging from a spring is stretched down 5 units beyond its resting position. So this is the resting position, and it's stretched down 5 units, whatever it happens to be, 5 centimeters, 5 meters, whatever, and released at time t equals 0 to bob up and down. Its position at any later time t is s equals 5 cosine t. What are the velocity and acceleration at time t? So you can actually figure out all of the equations, like with that s equals 5 cosine t, just from this Hooke's law. I'm not going to do that here now, but if you are super interested in it, it is pretty neat how you can get just everything that you saw about simple harmonic motion in physics class purely just from that equation and solving it. It's pretty interesting. So if you do want to see it, just let me know, and I'll make up a little video for it or just go over it with you in Zoom. But what we are given here is that s equals 5 cosine of t, and we need to find the velocity and the derivative, the velocity and the acceleration. Well, velocity is ds dt. It's the rate of change of our position. So derivative of 5 cosine t is negative 5 sine t. Right? Derivative of cosine is negative sine. So there we found our velocity. Next, we want our acceleration. Our acceleration is the second time derivative of position, which is just also the first derivative of velocity. So we can just take the derivative of this here. We're ultimately taking 2 derivatives of this, but the first derivative is that, and so we just have to take one more derivative again. So derivative of velocity, this is going to be negative 5 still. Derivative of sine is cosine of t. So there you go. Here's our acceleration. Here is our velocity, and there are functions for it. And then they are shown, or at least the velocity one is shown over here. The acceleration one, now you have to be careful because obviously velocity and speed are different units, so be careful that they're, the way you're drawing them. And then we'd have negative cosine. So if we were to draw that in, say maybe in green, it would do something like this, like that, and that would be our negative 5. This would be a, let me redo that. This would be a equals negative 5 cosine of t. Okay, but there you go, acceleration and velocity just from having our position function. All right, so the derivative of the tangent function here, derivative of tangent with respect to x, so this one is ultimately derivative of tangent of x is the derivative of sine of x over cosine of x, right? And anyway, it's just checking back. I thought it was one we had to do, but no, we didn't. So all right. So this is derivative of sine over cosine. So here we're going to use the quotient rule. So we're going to do the derivative of what's on top times what's on the bottom. So derivative of sine is cosine times the denominator minus the numerator times the derivative of the denominator. The derivative of the denominator, derivative of cosine is negative sine x. And this is all over the denominator squared, just like that. And so this becomes cosine squared x. And then here we have minus negative sine squared. So this becomes plus sine squared of x. Oops, this was supposed to be the denominator squared. All over cosine squared x. And now cosine squared plus sine squared, that's just a 1. And then cosine squared still in the denominator. And 1 over cosine is secant, so this is just secant squared x. So we get the derivative of tangent of x is secant squared. So that's one that you probably want to memorize, and you're probably going to do it so much in the homework that you won't be able to help but to memorize it, but that's ultimately what you get, is the derivative of tangent is secant squared. So you can memorize it, or you can get pretty proficient at deriving it out, just like I did right there. Okay, so if you look at this, remember this is our function tangent. It looks like this, right? Tangent looks like this. I'm not going to put in all the points, but this is what the tangent function looks like, right? This is tangent of x. And then what does secant squared look like? Well, I start with cosine, because that's the function we're looking at. So cosine looks like this, right? Maybe not so wonky on that side. This is cosine. And then I want to square it. So cosine squared, this is up at 1, and 1 squared is 1, so it's going to stay at 1s, but all the negatives are going to become positive, and so what you're going to end up with is something like, oops, messed that up, hold on, something like this. All right, here's cosine squared x. This is still at 1. This was at 1. And then now we have to take the reciprocal of this graph here. Remember, all 1s stay 1s, all 0s become asymptotes, all asymptotes become 0s, small numbers become big numbers become small numbers. So we're staying right here at 1, right? With all of these points right here, they're going to stay as 1s. So that stays a 1, that stays a 1, that stays a 1. These are where I had the 1s. There'd be another one over here too. Right? So you have all these 1s. Then we have all these 0s here. 0, 0, 0, 0. Those are going to become asymptotes. So right in between the 1s, we're going to get asymptotes. Just like that. And then our small numbers that are less than 1 are going to become big numbers. So these are small numbers in here. They're going to become big numbers. And the smaller they are, as this goes towards 0, it's instead going to flip up and go toward infinity instead of going towards 0. So it gets flipped over kind of like this. And we're going to have a bunch of these U shapes. Okay? And so this is secant squared x right there. Okay? So just there so you can see how to actually graph that. Next page, here are some more of these derivatives. You can go through and do them like I was doing before with the previous page here where we did the derivative of tangent. You can go through and try and figure out each one of these. Substitute in what they are actually in sine and cosine, and then use the product and quotient rules and stuff and solve these out. It's a good exercise to try and do. Again, you're going to use these so much that you're ultimately going to memorize them. But go through and do them, and see if you can come up with those, each one of them. But you need to at least know them. You either need to know them or how to come up with them pretty quickly, like I did on the previous page. So these are ones I find that while I'm working a lot and teaching this class, they start to stick in my head and I remember them. But if I don't teach this class for a few semesters or something, or I'm not doing them every day, I kind of forget them. But I can always refigure them out just by using what I know of as sine and cosine. Okay? Next, we want to find the second derivative of secant of x. All right, so we're going to start by doing the first derivative, y prime. Well, the derivative of secant is secant tangent. And now we have to do a derivative of a product. So the second derivative is going to be, we'll call this the first one and this the second one, is going to be the derivative of the first function. Well, the derivative of secant is secant tangent, right, times the second function, plus the first function, secant, times the derivative of the second function. Derivative of tangent is secant squared. And so what we'll end up with here is a secant x times tangent squared x, that's the first term, plus secant cubed x. And if you wanted, you could even factor out this and make this secant x times tangent squared x plus secant squared x. All right, and there you go. Make it look like something like that. Now, if you needed to ever, you can use one of our trig identities, which was secant squared minus tangent squared, sorry, with x's. That equals 1 is one of our Pythagorean ones, our Pythagorean identities. You can use that where you could do something like tangent squared x equals secant squared x minus 1, and you could substitute, you could substitute that in for tangent and get this in terms of nothing but secants if you wanted, or if you needed to for some reason. So be sure to go through and do that if you need to. All right, the last page here is stuff for you to try. Remember to use your trig identities. I'll have these all solved for you in the notes. Just go through and take a look and do them, especially number 59 there. This one's, you're going to want to look for a pattern here because you're going to want to compute a few derivatives and you're going to find that it starts to repeat. And so it'll repeat after every so many derivatives that you take. And so you're going to want to kind of figure out, according to that pattern, by the time you get to the 999th derivative, what would you be on? Which part of the pattern would you be? Where in the pattern would you be? And then figure out then what that derivative would be without actually doing 999 derivatives. You just have to do a few until it starts to repeat itself. Take the pattern and use the pattern to extrapolate out for what the derivative is. And again, I have that in the notes for you to look at if you want to see what it actually is. All right, that's it for this section. Thank you very much.